It's that time again, geometry students. Welcome to the lesson for 11.2, where we'll be talking about the areas of regular polygons. We know how to find the area of triangles, but there's a special formula for a regular triangle. There's a regular quadrilateral, which is a square. We know how to find the area of that, but we haven't had a formula, we haven't had a way to figure out the area of a regular pentagon, hexagon, etc. So we're going to find that out today, how to do that. So we need to know these things for this lesson. Make sure you understand those things by the time we're done, and using those extra examples in the book as we go along. So let's start off first with the area of an equilateral triangle. Remember, there was a theorem all back a ways where it said if you had an equilateral triangle, it's also equiangular, and vice versa. So equilateral triangle being also equiangular means it's a regular triangle. So there's a special formula that we can use as a shortcut to find the area of a regular triangle, an equilateral triangle in other words. And so let's draw a regular triangle. An equilateral triangle is also going to have all equal angles. Okay, so we have that going on there. If we called all the sides S, this formula is always going to work. We're not going to prove why this formula works. We could do that, but we're not going to take the time to do that right now. But it's S squared times radical 3 over 4. If you want to see the proof, let's put this in a different color. If you'd like to see the proof, go ahead and check that out. It's on page 669. Okay, so the proof is there. If you would find that helpful to look at that to help you remember why this works out, go ahead and do that. But it's based on special right triangles. You can make 30, 60, 90 triangles. We had that 1, 2, rad 3 thing, and it's kind of based on that, or it is based on that concept or that idea. Why don't we take a look at it real quick here, because I have the book pulled up, and so we've got 30, 60, 90 triangles. You can use those to figure out that that's going to be the same thing as what you see there. The book writes it as 1/4 times radical 3 times S squared. I read it like this though, because I think it's just an easier way to think of it, or to plug the numbers in. So I would say use this instead of what the book has written there, but they're the same formulas. So either way would be fine. If you like the way the book writes the formula better, it's an equivalent way to what I have. But for example 1, let's draw in a regular triangle, equilateral triangle here, 6 centimeters on each side. I guess I didn't have to label that all 3 times, but I just did, so they are going to all be the same since it's equilateral. We could use 1/2 base times height to figure out this, but we'd have to figure out the height first, and that would take quite a bit of time. But we've got the shortcut formula for equilateral triangles. Might as well use that here and just plug it in. So we have 6 squared times radical 3 over 4. That happens to be the same as 36. 6 times 6, radical 3 over 4. And this one you can reduce, because 36 and 4 have a factor of 4 in common. And so this would be the same thing as 9 radical 3. If you were to give this as an exact answer, you would leave it just like that. It's an area, so you would say centimeters, since the units are centimeters, you would say centimeters squared. If you were given this and you were told to get an approximate answer, let's just say to the nearest, my calculator, there we go, to the nearest 100th, 2 decimal places, we took radical 3, square root of 3, multiply that by 9, we would get 15.588. We would round that up to 15.59. So approximately 15.59 centimeters squared as an approximate answer. And so those ones should be, I hope, pretty straightforward, pretty easy to deal with. Now we get into, I think, the more interesting part of the lesson, but you may find it a little more challenging as well. Make sure you're paying close attention, even more so than you normally do. So I hope you normally pay really close attention as we're doing things. But like, take a $50 size circle, something like that. If you have coins, you could use a large coin like that. If you don't have that, just draw the best circle you can. And then I want us to draw a regular hexagon. So I think I actually have a tool. Yep, I can cheat, but you don't get to cheat. I'm going to make my hexagon the right size. It needs to be inscribed, so just touching all the sides there. Okay, so I've got that in there, and then I want to find the center of the circle. A little dot there. Looks like the center of the circle right about there. And I want to draw in a couple more lines. We're going to make a small triangle here, and I'm going to use my different color on one part as I finish this up as well. So let's draw in line there to there, and another line there to there. Pardon me. Let's call this A, B, keep wrapping your way around, C, D, E, and F. And then in your different color, let's put in one more that is perpendicular from there to there. And I want you to draw in a little 90-degree mark to designate that, or to denote that. And I also want to call the middle point G, and I'm going to call this point right here H, where that perpendicular part meets this side of the hexagon. And then in your different color, call this part little a. We're going to learn what that stands for. So that's a lowercase a. I put a little curl on mine, try to make sure it doesn't look like a 9 as much as I can. Okay, so this would be hexagon. This is just kind of some background information that we're going to need to know to be able to find the area of any regular polygon. This happens to be a regular hexagon, and it's A, B, C, D, E, F. I'm just listing the letters, picking one and starting going around, and that is one way to label that. So this is hexagon, A, B, C, D, E, F, and the center of this would be the center of any polygon, is the same as the center of the inscribed circle that it makes in terms of a, let's put regular. This is regular hexagon, A, B, C, D, E, F. So it has to be regular to say there's a center to the polygon, the center to this hexagon in this case. The center point would be G, because it's the center of the circumscribed circle, or the inscribed hexagon. The circle goes around and touches all those points. It has that center point for the circle, so the polygon has the same center point. This radius, or the radius of, you can have the radius of a polygon as long as it's inscribed like this. The radius would be a point from here to one of the vertices. So in this case, the radius would be GA. You could also say AG. You could say GB. You could also say BG. So all four of those would work. What it is, it's the center to a vertex of the polygon. So that's kind of the definition of a radius of a polygon. And then finally, I need to remind myself how to pronounce this word. Just a second. Okay, so I had it right, but I just wanted to double check and make sure. It's apothem. So the apothem would be G from this point here, the midpoint, and it's the point that's perpendicular to a side here. So apothem would be GH or HG in this case. So in other words, it's the center to a perpendicular point on the polygon. That's the definition of apothem. And finally, the central angle, well, it's an angle in the center. It would be AGB. You could say BGA as well. It would be an equivalent way to say that. Central angle is angle AGB. And so a central angle has the center point and two consecutive vertices. try to spell consecutive right there. There we go. Consecutive vertices of the polygon. And so notice here A, G, B. A and B are consecutive vertices, and it includes the center point of the hexagon as well. And it will always be 360 divided by n in a regular polygon. That comes from previous lesson, lesson 11.1. And so this angle right here in this case would be 360 divided by 6. I said that comes from lesson 11.1. It actually comes from earlier, so let's just get rid of that part and just say it's always 360 divided by n, because you can split this up. You can get 6 central angles. What I was thinking about was exterior angles, so that's a little different, but it happens to be the same formula. It happens to be 360 over n, because you can split this up into 6 different central angles. If it had 8 sides, you could split it up into 8 different central angles. Each angle, central angle, in the regular polygon will be the same. And then finally, for our final example, one more theorem. The area of a regular polygon. This is theorem 11.4. And what it says this: for a regular n-gon, there we go, n-gon with side length s and apothem A, this is the formula. A, capital A, standing for area, equals 1/2 the apothem times the number of sides times the sides themselves. This is the same thing as saying 1/2 A times the perimeter. So that's an equivalent way to say this. I'm going to write that down, or equivalently, whichever way you like better, whichever way works better for you, that's the way I want you to remember this. So 1/2 of A times ns, or equivalently A equals 1/2 of little a times P. And in a different color, please make this note here that these aren't two separate formulas. They don't say two separate things. This and this right here are the same things. NS is the number of sides times the side length, which is the same as the perimeter P. That's what the capital P stands for. Okay, so that's what those letters are. And I guess we said that up here too, so it's kind of like double hitting that. We know what all these things stand for based on that. Capital A is area, 1/2 of the apothem times the number of sides times the side length. And NS is the same thing as the perimeter. Why does this work? Well, if we go back to this picture, if we're going to find the area of this particular hexagon, in this case, this particular polygon is a hexagon, we could find 1/2 the base of each triangle here, with the central angle included in that, times the height of that triangle would be the apothem. So the base here would be the side length, 1/2 the side length, S times A, and then to find the whole thing, we would just take that and multiply it by the number of triangles we could make. We could actually make 6 triangles out of this, and so that's where this comes from. So it's basically, it is based on the area formula for any triangle is 1/2 base times height, and so that's really where this comes from. That's just 1/2 base times height times the whole number of triangles that you can make. So let's finish off with this example, and we're going to have example 2. I think that's worth noting though. Let's put this in, let's write this in with this. So this formula comes from the fact that area of any triangle is area is 1/2 base times height. And we can say in any regular n-gon, it's got to be regular though, you can make n congruent triangles So this is also equivalent to saying, I would also think of it as one other way we could think of it is that the area is equal to 1/2 times the base times the height, the apothem times the, I was to say the side length times the apothem, because the side length is the base. We go back to this, the side length right here, the S would be the base of this triangle and the height would be A. And so we'd have 1/2 S times A times, and you can think of this part as being the area of each triangle right here, and the N is being the number of triangles you can make. So notice it's the same thing as what I had up here. It's 1/2 just with the A, N, and S in different spaces or different places. So it's the same formula. It's just another way to think about that. I think it will all make a little more sense when we look at this next example. So let's get right into this final example here. You got a sandbox. Maybe you're playing it in a sandbox when you were a kid. Maybe you still do. I don't know. But this sandbox right here, this is boring. Boring sandbox. Boring. You are much more interesting than that. You're going to be a parent someday maybe, and you decide you're going to make your kids a sandbox. So I want to let's give this a little more background. Suppose you are making a regular, you're a lot more interesting than those boring people that make these boring square sandboxes. You want to make a regular heptagon sandbox for your kids. So we'll say it's for your kids someday. Regular heptagon sandbox filled with 1 foot of sand. So the question is, what's the area of the sandbox and how much sand is needed? So a 2-for-1 question. I want you to draw the best regular heptagon you can. So best regular heptagon, 7 sides. I think a good way to do this, draw a circle, a really nice circle. Maybe get out your $50 again if you got something like that, or a decent sized circle. I'm going to end up erasing this circle eventually, so do this lightly in pencil. Not my different color here. There we go. And then I think a good way to draw a regular, or a fairly accurate regular n-gon of any sort, is to draw in a circle first and then to plot where you would think the vertices would be. So try to split this 360 degrees of the circle up into 7 different parts like this, so I'm going to say that's 1, 2, 3, 4 should be a little more than halfway. So this would be the third side. The fourth side should be about halfway in between there and there. That looks pretty good to me. Okay. And so, yeah, that's going to be pretty good, I think. So if I connect all these now, I should have a pretty decent regular heptagon for this problem. And yep, that looks alright to me. So now I'm going to, as promised, get rid of the circle around that. So here's your regular heptagon sandbox. We're going to say it's not perfect, but this side is the same as this side, and so on. But these are all the same. And so let's put little marks on here. We'll include that. And let's call this SA. Oops. I'm going to keep this consistent with the way I had it before. Let's actually call this one A. That's N, D, B, O, and X, sandbox. And then I want you to draw in where the center of that regular heptagon would be. Come on, go away. There we go. Move that up just a skosh. I think it's pretty much in the same spot, but now we're drawing in one of the triangles. So notice you can split this up into 7 different triangles here. We could split it up into I've got one drawn, 2, 3, 4, 5, 6, and 7 different triangles. They all would have the same area, and so this basically is, that's another way to think of the problem. It's the area of one triangle and multiply that by 7. But in here, let's draw the apothem in our different color. So you want to find the midpoint right there and just connect these central point, or the center point, to that midpoint. Let's call this point in the middle C, and this point we're going to call H. And this is going to be a 90-degree angle right here. And let's put a little a for apothem right there. So if we can just figure out the area of this one little triangle here and just multiply that by 7, then we have what we need. So basically that's what I want to try to do here. I want to find the area of this one little triangle, multiply that by 7, and that's going to be the area of the whole thing. And so I want to draw this triangle again that I have here, just a little bit bigger and off to the side. And so I'm going to recreate that right here. This triangle is the same thing right here. And so this is H, the midpoint there. This is the center point C. In our different color, let's circle this part here and say that this is this part right here. So that I think that'll make that a little more clear as to what we're doing with this. And this would be S right there, and this would be the X right there, and the apothem, let's draw that in as well. Okay, so this is a right angle right there. Let's call that little a. So if we can find the area of just that one triangle here, we can find the whole thing. This is going to take some time though, because it's not easy to find the area of this, because I don't know the side length. Or actually, I meant to tell you the side length. I do know part of this. I actually know that the radius of this shape is 10 feet. So I forgot to mention that. So this right here would be congruent to this since it's regular. So let's put that in the drawing here and here. The radius is going to be 10 feet. 10 feet here, 10 feet here. But I don't know the apothem, and I don't know the side length of that. But I can figure it out based on, it's going to take from a lot of different things we've learned. So this is a deeper thinking problem for sure, but I don't think it's hard. You just have to remember a couple of things that we've already done in past lessons. And so right here, if we were to find the measure of angle SCX. We would know that would be 360 divided by 7. And 7, where did that come from? 7, this is the number of sides. So let's put that in a different color right here. That's the number of sides. That's coming from, one more back, there we go. That's coming from this idea. It's always going to be 360 divided by n in a regular polygon for the central angle. And so if we were to put this into a calculator, we would get approximately 51.4 degrees. So if you were taking this angle right here, trying to find the measure of that particular angle, that one is going to be the whole thing, SCX divided by 2. And so this would be then the measure of angle HCX. It's going to be approximately 25.7 degrees. There we go. So we just took that and we divided it by 2 because this central angle split it in half with the apothem. It's going to be that and that being the same. And so that's a pretty important piece of information right there. That's something we definitely need. I'm going to take now this triangle, I'm going to redraw one other part to this. You know what? I don't have to redraw this. I'm just going to keep using this triangle now, and I'm going to use what I've figured out here to figure out what A is, to figure out what the apothem is. And I can also use this to figure out the side length of one of these as well. And so be focused here. We just need to look at this picture and notice that we can use trig to actually figure this out. So we're going to say this one's 25.7 degrees and so is this one. Put them together, you get 51.4 degrees for the whole central angle. And so we can use trig to figure this out because we know an angle and we know one of the sides. We're going to solve for or find the missing sides based on that. And so I know based on trig that I could say I could use, this would be hypotenuse, and if I wanted to find the apothem I would be using adjacent and hypotenuse, which is cosine. So if I said the cosine of 25.7 degrees, that would be A adjacent over hypotenuse 10. So I could say A over 10. This is going to allow me to solve for the apothem. And so from here, I can multiply both sides by 10. I can say that 10 times the cosine 25.7 would equal apothem. In our different color, let's put that this is what we had originally. We multiplied both sides by 10. That canceled here. And that would be looking like that there. And so we would type that into a calculator. If you were to type that into a calculator, you'd end up getting your apothem as being approximately 9.0 feet. And so it's still not a final answer, but this is pretty important for us. This is going to be one piece of the information that we need to plug in into the formula here. So that you find the area of the triangle, area of a single triangle, multiply that by 7 in this case, and we're going to get the whole thing. So we need to figure out what the length of the side is from X to S. If we could figure out this part first, which we can do using trig, we can figure out this missing side and then just multiply that by 2 because the whole side length is twice as big as each one of these parts. And so let's do that here. Let's figure out that this would be, we could use sine, we could use opposite over hypotenuse. We know this angle, we know this would be opposite of that angle, and we know that that would be the hypotenuse. So we could say sine of 25.7 degrees would equal hx over 10. This is opposite and this is hypotenuse with respect to this smaller triangle right here. And so if I take this, do the same sort of thing I just did, multiply both sides by 10, get that to cancel there and there, and put this into a calculator, you would end up getting that hx is approximately 4.3 feet. So I'm just typing 10 times sine of 27 or 25.7 into a calculator. Because this is true, we would take this and we could think of it as this times 2. We would say that the side length, which is xs, is going to be approximately 8.6 feet. This times 2 is 8.6. So this is a side length. In other words, the lowercase s. So we figured this out, 4.3. The side length would be the whole thing, would be 8.6. So now I know the side length is 8.6. I know the apothem is 9.0. And if I take 1/2 of that times that, that gives me the area of this triangle. And if I'm just going to take that and multiply it by 7, because I can make 7 triangles that are congruent to that one, I have the area of the polygon. And so the area of the heptagon, now I'm going to think of that. I'm going to use the formula. It's the area of each triangle. I'm going to use this instead of this up here because it makes more sense to me to think of it like this. But you can use the formula like this as well. And so I can say I'm just ran out of space here. So the area of the heptagon is going to equal 1/2 the base times the height of the heptagon, 1/2 of the side length times the apothem, times the number of triangles I can make, times n. And so as long as you have s, a, and n multiplied all together times 1/2, you're going to get the right answer. But again, this makes more sense to me to think of it this way. This is the area of each triangle. I have approximated some things, so let's make this approximately equal to, this will be 1/2 of the side length, excuse me, which we found was 8.6, times the apothem, which is 9.0, times the number of sides, which is 7 in this case. If you multiply that all together, you end up getting approximately the nearest square foot, 271 feet squared. So this would be the area of your sandbox, and since the sand is only going to be 1 foot thick, the last question is actually really easy to answer from there. The sand needed is going to be the area times the thickness, but since the thickness is just 1, we're just taking 271, multiplying it by 1, and we have the same thing then, 271 feet cubed is the volume of sand we would need to purchase. It's a lot of sand, but you want your kids to have fun in the sandbox, right? Of course, of course. One more thing to write down is I understand that this one, we're going to practice this kind of problem a little bit more together, but I understand this one can be just a lot to remember in terms of, where did I get that from, or where does this come from? Just remember it's 1/2 times the base times the height of each triangle, and then just multiply that by how many sides you have, because that's how many triangles you can make. It uses trig, it uses central angle ideas from the first lesson in this chapter. Alright, I keep saying that from a previous chapter. Actually, it uses that 360 divided by n idea, but we're going to do a little bit more together, and I want you to check out, this is the last thing to write down here in a different color for me please, to see page 671. What is that? I don't know, I'm sorry. 671. Examples 3 and 4 for more like this one. Okay, so you're going to have to put some more time into studying an example like this. I feel, I'm pretty sure you're going to have to do that. It's a really good review question though of trig and some ideas about triangles that we've learned before and about polygons that we've learned before. Just putting it all together in this question. And so hopefully that helps you, and let me know in class if you have any questions. Thanks guys.